speaker, which is Manmeet Singh from University of Texas. He will present us about deep learning, augmented, numerical weather prediction, digital twin experiments for global precipitation forecasting. The floor is yours, Manmeet.
Thank you so much. And so the title of my talk is Deep Learning Augmented Numerical Weather Prediction, Digital Twin Experiments for Global Precipitation Forecasting. Now, when we talk about the global the weather prediction problem using deep learning, a lot of studies they would use convolution neural network, typically UNet. So this is one of the study which I am really a fan of. So by Wayne et al. In 2019, so they showed that we can build a deep learning system for weather prediction. The inputs would be time t and the output at time t plus 1. So they showed using geopotential height at 500 millibar and the temperature at 850. So those kind of self-sustained models which do not require a numerical weather prediction system. So this was like one of the I believe like one of the nice words. So then the next after that DLWP, the next thing that came up was so because of the sphericity in the data set, so there are bound to be a lot of spherical distortion errors that can come in when we are doing an image to image type of regression using a unit. So for example, if we plot the global data on a latitude longitude projection, then the mid latitude would correspond to, so they would be artificially enlarged, whereas the as compared to the tropics. But so they use this kind of a cube sphere projection, wherein the globe is considered as entire globe is considered as a cube, and we have the four faces along the tropics, so along the equator, two along the pole, and this kind of cube sphere, so the global cube sphere data set can be then opened as like six faces of a cube, which can then be trained in a unit. And one very cool thing that they used was that so traditionally in computer vision problems, the padding would be zeros, but in this kind of a global data set, we don't have a boundary. So they basically use this. So they basically use the boundary of the neighboring edge for doing the padding. Now this work, like as it was published in 2020. So this is where we start our work. Now these two works, DLWP CS and DLWP, they try to build a global weather prediction model using fields such as temperature and geopotential. But until these studies, like the studies prior to these, they would typically use limited regions, or they would not consider spherical distortion, which can lead to large errors in the prediction of the CNN. Or they would use simpler fields. So, for example, precipitation and soil moisture, they are quite complex as compared to geopotential height at 500 or temperature at 850. So we would need many more precursors for temperature, particularly for precipitation, and a system such as DLWPCS would require huge computational resources, and also it would not take into the benefit or of the numerical weather prediction, the success that numerical weather prediction has shown us. So there is basically a system for global precipitation forecast, which can be considered as a digital twin of the real system is required. Now we modify the DLWPCS from a temporal mapping to basically a spatial mapping. So for example, Now we have to think in terms of how a numerical weather prediction model that generates the precipitation. So there are these partial differential equations which solve for the wind, for the temperature. These are the coupled equations which solve do integration and using the various calculus operations. They calculate these fields, and then we have the parameterization which take in the inputs from temperature, from winds, and then they generate precipitation. Now we what we are saying is, so then, like, building a system wherein we can take in as input the different fields which are good precursors of precipitation, and doing the mapping at the same time step. So for example, temperature, so global temperature in cube sphere to precipitation, and total cloud cover to precipitation. So variables which have good links to the precipitation that has been shown in the past physical studies. So in a proof of concept work, we basically use the weather bench dataset, and which is derived from ERA 5 reanalysis, and we take the hourly dataset for training. So we build two models. One is using the total cloud cover ERA 5 as input, and the precipitation data from ERA 5 as the target. And another model, deep learning model, we take the surface air temperature as from the weather bench, and precipitation as the target. So the training is from 1979 to 2009. The validation at the time of training is from 2010 to 2011, and the testing is for 2012 to 2015. So next, I'll show some results from the proof of concept of our model. So we can see that the median for day one precipitation. So we are for this case, we are not considering the time lead of forecast. We are concerned about, like, how in the model there is some missing physics, or the models are not able to correctly map from the different fields to the precipitation. So we saw we are calling it day one median. So we can see that the distribution of the ground truth, or which is the weather bench or ERA 5 reanalysis, and the GFS model, which is used for the forecast. It's used operationally around the world. Our deep learning models are comparable to the GFS and to the ground truth. And when we built a linear regression model, that was showing something which is very bad. So that's the first check of sorts. Next, what we did was we took this date, 1 day lead prediction from GFS model, and 1 day lead we can consider as the initial conditions would be like, or the fields, other fields which are leading to the formation of precipitation, they would remain almost similar. That's an assumption we are keeping. So it would be assuming that it's at the same time step, but it is something which the parameterization is generating. And then we have the correlation, the grid point correlation from our model DL1 and DL2, and this is for the linear regression. So we can see that for the global land areas, the GFS model shows a correlation between the model predicted values and the ground truth to be somewhere around zero point 0.2 to zero point 0.3, whereas we get values around 0.5 to zero point 0.6. Now this is still at the proof of concept stage, and then we also compute the over important land areas. We compute the area average correlation. So that is also something which the deep learning models are showing us substantial improvement relative to the GFS baseline. So then we are also building a product based on this proof of concept. So we have taken the North American multi-model ensemble CFS P2 hindcast. So this data is available from 1982. So that we have taken is from 1982 to 2010, and it is a 6-hourly product. So we aggregate it into daily. So lead 1, lead 2, lead 3. and lead 3 days, and then we so this is for the temperature and for the model predicted temperature and model predicted precipitation, and we take the target as the weather bench or era 5 reanalysis precipitation. Now we first do would normalize and we would generate the cube sphere, and then we have the unit. So we take the training period as 1982 to 2000, and the hindcasts they are initialized every 5 days. So the data set is available actually available until 10 months lead, but the we have a new model simulation available which starts every 5 days from 1982 to 2010. So we divided it into like 1982 to 2000 is the training period, 2001 to 2002 is the validation at the time of training, and we took the 2003 to 2010 as the test period. And then after prediction, do an inverse mapping back to the latitude longitude grid, and also then renormalize to the hypothesis is that we should get better result or better output as compared to the CFS V2 handcuff. So here we plot for the test period the which is 2003 to 2010 is the model as not seen. The mean of the bias for the month TJF. We also check for January, February, so separately for other months, other seasons, and it is the performance is similar. So we can see that at 1 day lead, 2 day lead, and 3 day lead, the model, the numerical weather prediction model, it basically highly overestimates precipitation over land, whereas our model, which takes in the input from the numerical weather prediction model, and the labels are the era 5 precipitation. So it does a reasonable job in bringing the bias. So this is the mean bias down to somewhere around like within the range of -1 to 1 +1 millimeters per day. And then the next thing is we also check with specific cases. So for example, so we have checked multiple cases, and herein I'm showing the South Asian extreme rainfall, which also which was on 26th of July 2005. So so in this case the CFS model starting from 25th July 2005 is considered, and so 26th July 2005 would be lead 1, 27th July would be lead 2, and 28th July would be lead 3. So there are heavy rainfall over the western coast of India, and which led to massive flooding and loss vast large number of losses. So we can see that the era 5 it is showing us that the precipitation happened mostly over around the central part of the central Indian region and over along the western coast. So we can see for the 26th July and as well as for the 27th July and also for the 28th July. But the CFS V2 model is heavily overestimating. It is raining over the Arabian Sea and over Bay of Bengal, and it's all over raining, and the bias is too large in the CFS V2 model, whereas we we are not able to get the exact absolute values of the extreme rainfall. However, we are able to substantially correct in the spatial pattern of the precipitation. So for this particular example, for lead 1, lead 2, and lead 3. So we are still doing this work, and this is a part of the ongoing work using this model. So to conclude, we have developed a framework for fast and reliable global weather forecast, and the system performs reasonable in a theoretical setup. There are some issues with the absolute values of extreme precipitation, and that I think is because like this, if we increase the resolution or add more variables or change loss function, that we're still working on those aspects. And as has been shown, it can be easily transferable to build a hybrid uh, deep learning plus NWP product. And the preliminary results show us promising are promising. So thank you so much for your time. and I would be happy to take any questions.
Thank you very much, Manmeet. I have maybe one question for you and start till we have some more from the audience. Regarding data splitting, as I know, you split data based on temporal splitting. So in the beginning, validation, training, validation, and testing. I would like to know what's your opinion if this maybe could be maybe not so beneficial in terms of, there are trends in the data, which make it maybe more difficult for the model to really understand compared to the past or the present, climate. You had maybe a more, random splitting somehow.
Yeah, so actually, yeah, that's right. I agree with that. Like, since, yeah, I mean, we are working on k-fold cross validation, so doing random splitting and using different data sets for training and testing. Yeah, but yeah, so that would that I think yeah, we'll consider that. So that still has to be done.
Thank you. We have one more question from Matthew. So the question is, how do you handle the time dimension in your architecture?
So in the model wherein we are inputting the CFS V2 model outputs, we are taking the channels, the different times as the channels of the unit, and so three channels for the precipitation, three channels for the NWP model temperature, and the output is a three-channel precipitation. So that's how we are handling the time steps in this.
Thank you. Maybe can you maybe elaborate more regarding the seasonality on the results and how it affects, if it's much or if it's not so much? Yeah.
Sorry, can you? I was, yeah.
Yeah, sorry, I was meaning for the seasonality. So, for example, DJF or JJA, if there are some differences.
Yeah, so we have, yeah,
what?
So we have seen that like for example for JJA, there is a monsoon over South Asia, so there is a large bias, positive bias in the NWP model that we see, and which is, so the results are similar in a way that this modified DLWP-CS, it reduces the errors in the NWP model output. And we have also checked with the, like for example, South Asian extreme rainfall. We have also checked with China floods, with Hurricane Ivan, Hurricane Katrina. So the NWP, the CFS V2 model, it's out, like it's showing a wet bias at these short range time frames. So yeah.
Thank you. We have one more question from Matthias, which says, exciting stuff. How relevant do you consider the cubed sphere representation?
I think that's a very important aspect of this work, like because the traditional CNN would basically assume it to be the global data to be a 2D image, whereas actually we should use a spherical CNN in this case, and and that would actually induce a lot of errors in the mid latitude, like in the teleconnections. So this is I think this is a very important component of this work.
Great, thank you very much, Manmeet. Here, maybe I would like to mention also that there were some questions for the previous presenter that now we have the answer to the Slido for the ones that want to have a look at the answers. And now we can move to the next talk,